Hi, I'm Tristan Morales, and today I'll be conducting a presentation over an untapped resource or an unknown resource known as carbon. Basic Energy Science course, or the course that we're in, is actually one that has left us with many answered questions. We have gone over the many concepts of different forms of energy between the urban and all environments throughout the world. This includes the use of natural gas, fossil fuels, or nuclear, wind, hydro, and so on. Amongst all of this, I realized that there were some commonalities between all the topics. Carbon dioxide, aka carbon, which is a chemical compound that is actually known as a greenhouse gas, and there's a large quantity of it in our atmosphere. Due to these similarities between all the concepts, this has led me to conduct my research project over this compound because there is a vast amount of it in the atmosphere where it resides to this day, along with the creation is still occurring to this day. Carbon technologies are not a new concept. The idea of carbon captured and usable technologies date back to the 1920s and have later been refined in the 1970s. This includes sequestration, where carbon is actually harnessed / cut off from the atmosphere and put into some sort of machine or sectioned off. This is the main topic or technology that we will actually be discussing throughout this presentation, as usable carbon is still something that is greatly in progress. Plus, this is actually the first step. So in this slide, we actually observe what a DAC infrastructure could look like. Just note that this is a large array of fans. It can come in the form of a larger building or like a power plant looking site, or even a structure that looks partially underground. But this is the rapid deployability version, meaning it can be set up in a given location. So a little bit of background is that it's actually relatively newer. Most of the DACs are a large array of fans, as you see in the image, and these fans actually act as a vacuum cleaner that pulls in raw atmospheric air, sends it through a couple of pipes, which eventually come in contact with a potassium hydroxide solution. That solution forces the CO2 particles to bond with it and ejects the rest of the remnants of the air out. So those CO2 particles come in contact with a lot of heat and pressure to the point where they become salts. After the initial salt phase, it undergoes more heat so that it can become purified carbonic salts, where we will put the carbonic salts into a pellet reactor, which breaks them down into carbon and then other impurities. And that pellet carbon actually comes in contact with a calciner, which forces it to release a purified gaseous form of carbon dioxide. And that carbon dioxide is actually generated or pushed into the ground. And the rest of the remaining pellets get recycled and reused for the next phase of the process to start over again. So to simplify the last slide, I made up these 3 little steps about how the carbon is actually extracted and what the end goal is. So carbon is actually taken from the air in the atmosphere, the air we breathe. That carbon is then mixed in with a solvent or compound liquid so that it can be superheated and undergo massive pressures until the purified carbon is separated and formed. The pure carbon is then injected into the earth or stored for other purposes, but the point is that it's no longer in the atmosphere, where it can contribute to the rising temperatures or any problems revolving around carbon dioxide in our generation. So on this slide, we'll be looking at the perks or the advantages of a direct air capture carbon technology. The main point is that it'll slow down the ongoing carbon dioxide crisis. So short story is that the Earth's average temperature is gradually increasing. If we eventually hit a 2-degree average increase in temperature, we could potentially looking at global crises regarding climate change events. So capturing carbon dioxide and storing it away gives us a potential way or solution to combat this ongoing problem, so that we can slow down what's actually affecting us in a later situation. Another perk about this is it's highly mobile or deployable. This is great because we will be allowed to move around these facilities to nearby towns or cities so that they do not interfere with public infrastructure or life. or we can even put it in areas with a heavy carbon dioxide concentration if needed, so it doesn't affect the human life over there. Next, we have it creates potential waste for carbon dioxide. So this is actually great. There's much or a lot of carbon dioxide inside of the Earth's atmosphere. So as humans constantly depending on electricity, this should kind of give us some indicator that we should be looking at carbon dioxide as a fuel or an energy source. So I'm sure that with the capture or the storage of this carbon, technologies running on carbon dioxide will eventually be created or improved. Next, we have the storage process. So not releasing carbon dioxide is actually great because we don't want to just get rid of the process that we just went through. So when we store it, we cement it off and seal it so far underneath the earth to the point where it will not get released for several generations or will not impact the earth for much more time beyond humans. And then lastly is not a large footprint. So this goes back to the infrastructure. In the event that we did have to put one of these facilities in a city, the facility itself is not actually that large to the point where it'll interfere constantly. There might be some noise with the fans, but I mean, it'd be a better trade-off to get rid of the carbon dioxide than just a little noise like a freeway or a highway. So that's one of the great things about this. So on this slide, we actually see what the end goal or the present advantages could be for the DAC machines. And over here we have a DAC and we see it converting to the raw or purified CO2. So in the future, the end goal is to make fuel out of that CO2, and then we could see it be put into vehicles and then made into CO2 again, where the cycle begins over again. On the right side, we actually just have an image, a representation of taking the CO2 out of the atmosphere and making a more green environment. But looking at some of the cons for direct air capture technology is that it's very expensive. Not many companies have invested quite into the idea, let alone know anything about this type of technology. So right now we'll be looking around $200 to $600 per CO2 ton stored inside of the earth. And it becomes expensive due to the intense heat, compression, or even those pellets that I mentioned earlier, with the exclusion of one company, but we'll go over that later. So that means that the technology is still in its early phases for most companies, as many companies won't share their information because it's for money. So moving on to the next one, it does not eliminate or create negative carbon emissions. So this is actually a really big deal because the world's population is growing and the use of automobiles or private automobiles amongst that population is also growing. This is only creating a larger carbon dioxide problem than that of last decade. And this technology is not at a stage yet where it can handle that extra amount of carbon dioxide. So this is merely a way to combat it, but does not eliminate carbon dioxide as a whole. Another big con about this is it can require land use. As I stated in previous slides, fans can make large noises, or it can even be a minor inconvenience for a structure like this to be set up for human life or even other life. So it still takes up land, and that land needs to be appropriated for this type of technology. And then again, large amounts of energy required. This goes back into expenses, where large amounts of heat or electricity still need to be used for this process to work. And if we're not careful, depending on the energy source used, we can create more emissions than what we put back into the earth. Lastly, other deposits on this slide. So in order to store that CO2 in the earth, we have to drill a pocket into a well, kind of like hydrofracking, except we are storing CO2. If we hit another pocket of something else, we could be looking at a natural gas emission or ejection back into the earth, in which we created a problem that larger than the one we started with. So that's it for the negative impacts. And just in case you didn't get some of those concepts down, the biggest ones is that it costs a lot of money, much energy or electricity in this case, and that it will still be producing carbon if we were to use this machine on a wide scale. So with all that in mind, moving along to the implementation of DAC, these are some major things to consider. As of right now, there are only a handful of companies actually addressing the carbon problem. The major one that could potentially be on top is carbon engineering. So a little bit short story, that cycle that I showed you in the earlier slides is actually derives from carbon engineering, as they are the most effective company right now in carbon sequestration, storage, putting away in the earth. They claim to put away 1 ton of CO2 from $90 to $210, while the other companies kind of hang around the $200 to $600 ballpark areas. So that's pretty important, and they found a way to do it efficiently and save money in the same time. Other things that would need to happen is further research amongst these smaller companies, or federal funding with these smaller companies, even carbon engineering, because there is much to be understood when it comes to this type of technology, and we're still very much in the proprietary phase. A national collaboration would have to happen. So this is one thing that should actually be spread to the rest of the world. As you know, the United States is not the only entity responsible for creating carbon dioxide emissions. It should be a world problem, and the world needs to address it. So that can happen through the United Nations or any sort of major national collaborations. Awareness, again, the national collaborations would be a great way to start doing that. All right, so bringing it back to Homeland, potential incentives through the government for improving this technology. So companies don't want to lose money. That's the biggest thing when it comes to new technology, let alone technology they don't necessarily understand. With the government backing these types of studies or research, we could actually see an increase of improvements for this kind of technology. Incentives can be given in the form of tax breaks, grants, additional funding, or even stipends. Things like that need to happen. That way companies don't see it as a total loss. They could see as a way, they could see the funding as ways to make up for some of the loss that they have. So I think that would kind of help out when it comes to the involvement of this kind of tech. And then lastly, I absolutely believe that the major energy giants need to get involved with these type of projects, because the end goal is for carbon to potentially be used as fuel. Well, if other companies start seeing that, they would probably like to start investing in this sort of idea. But the first step will be the direct air capture method. So in order even to achieve carbon dioxide as a fuel, we need to take the first steps in exploring this type of research and see what we can actually do with sectioned off carbon dioxide. So if there are no further questions, or if anyone has a question, feel free to reach out. This is actually concluding my presentation. And then here's my works cited. Thank you for your time.